My name is Paige Allen, and today I'll be talking about Lab 3, Black Holes and Orbits. Just the general agenda for today, I'll be talking about the introduction or purpose of the lab, some background physics knowledge, my codes, and the potential errors and concept question answers regarding this lab. So this lab is composed of two main parts. The first part wants to determine the mass of a black hole by analyzing the motion of a star. So in this case, our system would be the star and the black hole, and the environment would be space. While part 2 aims to find a trajectory for the spaceship that has some sort of figure-8 orbit around the moon and planet. While that may not be possible, the overall goal actually is to find a motion of the spaceship that will be influenced by both the planet and the moon. So you would need to find some sort of speed that has that influence while being able to orbit without crashing. Both labs require the use of GlowScript, a VPython program. And I don't think I mentioned this, but the part 2, the system would be the spaceship, the planet, and the moon, and the outside factor would be space. The black hole is not considered here. So the two main concepts explored in this lab are Newton's second law and gravitational force. On the left-hand side, you can see that second law equation, F naught equals ma, is actually can be rewritten to be the change of momentum over change of time. And what's interesting is that this can actually be composed into its parallel and perpendicular aspects of momentum. And these perpendicular and parallel components are actually what make up the net force. So we can actually analyze this or view this by breaking it down further into components versus overall net force. On the right hand side, you're going to see the gravitational force, which is equal to the gravitational constant times mass 1 times mass 2. In this case, that would be the star and the black hole over the radius squared. And you can actually rearrange it to be able to determine the mass of the black hole to be the change of momentum over times radius squared over the gravitational constant times the star's mass. Those two were both reflected here in the part 1 code, so you can actually see that the first few lines are what compose and create the change of momentum over change of time, and then we use Newton's second equation to be able to determine that F naught is equal to dp dt. And then it was further broken down into its parallel and perpendicular components, which were actually shown on the arrows on the code to the right. So you can actually see that the cyan is representing the perpendicular, the magenta is representing the parallel, and both of them are affecting the net force, which is the orange. The mass of the black hole was determined to be found around 8.56 times 10 to the 33rd kilograms. Part 2 of the code pretty much relied on a lot of known values. So to be able to calculate the radiuses of each of those, we just use those known positions and found their differences. For the F net of each of those interactions, we use the gravitational force equation. And then we applied Newton's second law using like the velocity update and position update formulas to be able to calculate their specific trajectories. This is the code that was reflected through that. And you can see on the right-hand side, the navy blue is the planet, the cyan is the moon, and the magenta is the spaceship. And at no point do they actually end up crashing and ending the code. Some of the potential errors and limitations to this lab are the code only considers perfectly stable conditions, so it does not predict chaotic motion or general relativity, which could very well change any accuracies reflected in this computational model. The tidal forces between the moon and the planet are not considered. They also may be very limited in this equation. As you can see that there is some bit of change to the trajectory of the spaceship, but not enough to show that there's a great gravitational tidal force between the two. And then the given values were under certain parameters, which do not reflect anything that could be an external force, such as the black hole that was previously mentioned in part 1. In terms of accuracy as well, finding the velocity that would be able to yield that code was a trial and error process. Different values will create different trajectories, and there could be better ones that create one that is within proximity to the moon and the planet, or there could be one that creates more of a figure 8. But for the purpose of this lab, the velocity I had chosen had successfully done its job. Just the concept checked and Q&A. One of the questions asked about the net force versus the rate of change of momentum. Mathematically, they are the same thing, but the net force requires you to know all the individual factors on the system. So you would need to know every individual net force interaction created. While the rate of change only requires the system's change in velocity, which is a lot easier to calculate and predict. To be able to predict the motion of the entire system, however, you would need to know pretty much all the given masses, positions, and velocities, the interactions between each of those objects, and the motions prediction using the second law of Newton and time step updates. To be able to determine what is the dominant interaction, it depends on mass and distance of each of these objects. So the black hole, having that value of 10 to the 33rd kilograms, has the greatest mass and could be the most dominant, followed by the star's mass, planet's mass, and moon's mass. But you do have to consider the distance between the object in question and each of these interactions, which could change the dominant interaction greatly.